Hey guys, welcome to recitation number 10. So we will solve, probably you have seen the last lecture, we talked about some special things in linear algebra, such as Jordan decomposition, or about simultaneous triangularization or matrix diagonalization, some things that you will not see in a usual linear algebra class. And today we're going to start solving some problems, so let's get started. And I'm going to solve some problems involving eigenvalues and these new techniques. So the problems that I will solve are the last problems from 23 to 30. Well, I'll solve some of them from the worksheet. And the first problem is the following. Let's just say problem 1 for today. So it has the following statement. So let M be a real n by n matrix with all entries in this set. So in the set of 0 and 1, right? Such that all eigenvalues are positive. Prove that all eigenvalues are equal to 1. Okay, I want you to look at this statement. So it's problem number 23 in my worksheet. It's a very nice problem. And let's see. Well, usually I should have told you what problems to think of. But anyway, you see, I have a real n by n matrix. So let's look at this. So a real n by n matrix. So let's just say that this matrix is something like has these entries I, A, J, with I and J going from 1 to n, right? And these numbers I, A, J are real numbers, right? Okay. And all the entries are 0 and 1. So these entries, in fact, let me just I can say that are in 0 or 1. But I have another information here that all the eigenvalues are positive. So now let's so let A and lambda 1, lambda 2, lambda n be the eigenvalues of A, right? So now there is a way for you to relate the eigenvalues and the do you know how you can relate the entries, or I don't know, the sum of some entries of a matrix with its eigenvalues? Do you know there is a way? So what is that special thing that you need to do? Is by taking the trace, right? You know that the trace is the sum of the elements on the eigenvalue, on the sum of the elements on the main diagonal, and but also the trace is also the sum of the eigenvalues. So we know that the trace of A, so let me write it, is the sum of these elements, right? of these entries, AII, right? The entries on the main diagonal, but also we know that this is nothing else than the sum of the eigenvalues, right? Okay, so I know this, but look at the entries. The entries are in that set 0, 1. So what can you say about that sum? About the trace of A, basically? It can be between something, right? What is the least possible value for the trace? When all the elements on the main diagonal are 0, correct? So all the AIIs are 0. So in that case, the trace will be 0. And what is the largest possible value? Is what? N, correct, right? So it's N. So this will happen when all the elements on the main diagonal will be 1. So we know this. So let's see. Clearly, the trace of A is less or equal than N, right? So the sum of the eigenvalues is less or equal than N, because we know that that's the trace, right? Okay. All right. Okay. All right, so that's the first thing that we know. There is a trace. Is there another thing that we can relate the eigenvalues and maybe some also the sum of the elements of the matrix? What is the other thing that we can that relates that?
Are you talking about specifically just the diagonal elements or just the elements in a
Elements in general. Well, in this case with the trace, it just happened to be diagonal, but there is another thing that.
Well, isn't the determinant like a sum of products?
Exactly. So is the determinant. But we also know that what do we know? That the determinant of A is, you know, the definition is the sum of the IAJ times the complement, right? And these complements are just some matrices, minors, -1 to the power A plus J times the minor, right? Which is a determinant, an n minus 1 determinant. So sum over all IJ. So what do we know about this? That these guys, right, are 0 and 1, right? So you can say that or maybe wait, I think I made a mistake here in the statement. I think the entries are real or now, okay, the entries are 0, 1. So what can you tell me about the determinant? Right, so keep in mind that the entries are 0, 1. So what values can the determinant have? Since determinant is that sum aij times the complements, right? So these are where these guys Cij are the complements. So they were this is the ijth complement. of A. So these Aij, keep in mind that the entries are 0 and 1. So these, well, the determinant, well, not all of them can be 0, but you can say that the determinant will be positive, right? So that of A is greater or equal than 0. You can definitely say this, right?
Do you have to be more specific and say non-negative? Because can it be 0 as well?
Yes, non-negative, yes, non-negative. Yes, it can be 0 as well. So this is non-negative, correct? You agree with me so far? Okay, but now, again, the determinant of A, can we relate this in terms of the eigenvalues? Yes, we can. So this is nothing else than just the product of the eigenvalues. Okay, let me put the same. It's I lambda I. But we know that the eigenvalues are positive. So the determinant will be positive. Okay, so I know that all these eigenvalues are positive. But now, there is one thing that will, but now by the AMGM inequality, there's one missing ingredient. So by the arithmetic geometric mean inequality, we have, so let's see, what do we have? So we have that lambda 1 plus lambda 2 plus lambda n, everything over n, is greater or equal than the nth root of lambda 1, lambda 2, lambda n, right? Okay. Okay, but now I know that the sum of the lambdas, look here, I obtained this inequality here. This will be less or equal than n over n, which is 1, right? But on the other hand, this guy here, so it follows that the product of the lambdas is less or equal than I. But this is nothing else, or the determinant of A, is less or equal than 1. But the determinant of A is non-negative. And by the way, there is one thing about the determinant you need to know, and that was it's not that it is a non-negative, it's also an integer. That's a very important thing. This guy here is an integer, right? It's a non-negative integer, but it's a non-negative integer, but not just non-negative, since all the eigenvalues are positive, it's a strictly greater than 0. On the other hand, the determinant of A is positive, and the determinant of A is an integer, positive integer, in fact. But I know that it's less or equal than 1, so the determinant of A has to be 1. But this implies that we have equality in arithmetic geometric mean inequality. So this forces the equality case. Oh my God, there's politics involved here with the election and everything. Just pops up on my YouTube. So this forces the equality case in the above inequality. right? When do we have equality in the arithmetic geometric mean inequality? When what? When all the eigenvalues are equal, right? Which means that all eigenvalues lambda 1, lambda 2, lambda n are equal. But we know that all the eigenvalues are cannot be, and when this happens, which implies that all of them have to be equal to 1, right? Lambda I is 1 for all I. And that's it. Is it clear for everybody? Jack, is the problem clear?
Yeah, I think I get the general idea. So in this case, the when the lambda values are equal to each other, they're equal to 1, right? So
Yes, yeah, there cannot be other value because look, we got that is less or equal than 1.
Yeah.
It will force to be equal to 1. And also the trace is less or equal than 1, so all of them have to be equal to 1. There is no other chance to. Is it clear for everybody?
Yeah.
Okay, tricky.
Yes.
Right? Very tricky problem. But it's a nice fact to know that if you have a real n by n matrix with entries 0, 1, this is a special type of matrix, right? When we have one of them is 1, the other one is 0, but you know that all the eigenvalues are positive, then all the eigenvalues must be equal to 1. And in fact, not just that all of them equal to 1, you can say that the determinant will be 1, the trace will be n, and so on. So that's a very important fact. Okay, it's a very nice problem. So I want you to keep in mind this technique. Now let's veer towards another problem. So problem 2, which says the following. So problem 2 is, so let's consider this matrix A in an n by n matrix with real entries, such that the trace in absolute value, that the trace of A is greater strictly than n. Show that A to the power k is different than n to the power p for all kp positive integers. And k is not equal to p. Okay. I want you to look at this problem for a bit. We did a similar problem for 2 by 2 matrices, if you remember. Remember that problem that we did when we actually proved that in 2 ways. When I have a 2 by 2 matrix and the trace of the matrix in absolute value is greater than 2, strictly greater than 2, then A to some power, an integer, positive integer, will always be cannot equal the identity matrix, right? I think it's in lecture, I don't know, I think in the first week of linear algebra. I don't recall exactly in which lecture, but you can find it there. So maybe we can use this similar idea here. So let's see. What can we do? So let's assume by contradiction that that a to the power k.
Oh, sorry.
Say that, yes, Aaron?
Oh, I was just gonna say, would you assume for the contradiction that there exists some KP?
Yeah, exactly. A to the power k is a to the power p for some positive integers. Kp, right?
And the trace has to be greater than, the trace of A has to be greater than N, right?
Yes, we know that trace of A is greater than N. So we'll like to use that. That's a very important piece of information. So let's look at this guy. But now I'm trying to deduce something about the eigenvalues of A. Can you tell me something about the eigenvalues? Given the fact that a to the power k is the same as a to the power p, what can you tell me about the eigenvalues of A?
They have to be the same, right?
Not quite, but something like that. What can you tell me? So it's a is if a to the power k is the same as a to the power p. Can you tell me something about the eigenvalues? So let's see. Well, it will follow that if lambda is an eigenvalue for a, then lambda to the power k is the same as lambda to the power p, right? So let's see that. So if lambda is an eigenvalue of a, right? So so we know that then from the definition, then from the fact that ax is the same as lambda x for some vector, which is different than the column vector, right? Let me put it like this. So O and 1, so it has one column, right? From the definition, it follows what? It follows that a to the power k, right, x, is lambda to the power k x, right? You just iterate this. And a to the power p x is the same as lambda to the power p x.
I have a question.
Say that again?
I have a question.
Yes.
Does this have anything to do with the unitary matrix and the, like where if?
No, it's just the definition of the eigenvalues and eigenvectors, basically.
Okay. All right.
So we say that lambda is an eigenvalue for a matrix A if there exists a vector, let's say x, which is different than the zero vector, such that ax is lambda x. And we call that vector to be the eigenvector associated to that eigenvalue lambda. So basically, I'm just applying this definition and I'm just iterating it, right? So a to the power k, so you multiply by a, but then you get a squared equals lambda equals a lambda x, but you know but lambda goes out, it's a constant, so it will be lambda ax, but you know ax is lambda x, so you get lambda squared x, and you keep iterating like this, so inductively. So you'll get that a to the power kx is lambda to the power kx, and the same goes for p. And now, since you know that a to the power k is the same as a to the power p, it follows that. So lambda to the power k is the same as lambda to the power p, right? So if you take the absolute value, and this implies that lambda to the power k is the same as lambda to the power p. So what does this mean? This means that you have only two options. And it follows that. So this will give us that lambda has only these possibilities, 0 and 1. That's it. But now, since lambda is between 0 and 1, so, but by the triangle inequality, So by the triangle inequality, what do we have? We have that, what do we have? We have that the trace of, so n, which is less than the absolute value of the trace of A. And you know that the trace of A is the sum of the eigenvalues. So this will be lambda 1 plus lambda 2 plus lambda n. It'll be less or equal by the triangle inequality. So here I apply the triangle inequality, then the absolute value of lambda 1 plus the absolute value of lambda 2 plus the absolute value of lambda n, right? But these guys are just 1, 0, and 1. So this will be definitely less or equal than n. This is a contradiction. So we obtained a contradiction. And this contradiction will what did the contradiction come from? So it came from the fact that we assume that a to the power k is a to the power p for some positive integers, k and p. So we obtained a contradiction. And that's it. Right? That's the problem. Is it clear for everybody? Right? So it's just a triangle inequality. It's basically the same idea as we did for that 2 by 2 matrix problem. Okay.
I have a question.
Yes, please.
The sum of the eigenvalues, or the sum of the absolute value of the eigenvalues at the end there, why is that strictly less than or equal to n?
Greater than.
We're arriving at a contradiction here, right?
Because it's the eigenvalues, look here. Less or equal than n. Look, there are 0 and 1. So it can be at most n.
Gotcha.
So each eigenvalue will be at most 1. So it's less than 1 plus 1 plus 1, which is n. But it is greater than n because we know this from our assumption here, which we get n less than n, which is a contradiction. It's clear now?
Sorry, so you're saying that n is less than n is the contradiction there, essentially?
Yeah. N cannot be, n is strictly less than n.
N cannot equal n is the contradiction at the end there, because it has to be less than n.
Yeah, exactly. You don't have, you see, here you have strict equality. Look here. So here you have strictly less than, without equal. So it's n strictly less than n at the end. So n is strictly less than a quantity, and this quantity is less or equal than n, but this is a contradiction. Anyway, now let me do another problem. And in fact, this is problem 28. So let's see problem 3. And in fact, here we will use some of the notions that we learn in, I would like to do this. This is a very nice problem. The problem says the following. How should I say? Okay, there are 2 parts here. So part I, it says the following: let n be mn, so it's an n by n matrix with complex entries, but more than that is a nilpotent matrix, so be a nilpotent matrix. And we would like to show that the determinant of the identity plus n is 1, right? This is the first part. And the second part says the following: let A be, I have 2 matrices, n by n with complex entries, right? Such that they commute, such that AB equals BA. And remember, last time I told you that something happens when the 2 matrices commute. You can do basically pretty much everything you want. You can simultaneously triangularize them. So in fact, that's what we're going to do. So that will be, this is an important condition.
So I have another question. So if they commute, can you do the eigenvalues, like the operations on one, translate over to another?
Yes, exactly. Basically, you will say that the eigenvalues of A plus B are the eigenvalues of A plus the eigenvalues of B if they commute.
Gotcha.
And the same you can say for the product, right? So you can say that the eigenvalues of pretty much, the basically the characteristic polynomial of A and AB and BR is the same. But anyway, you can do even more. You can simultaneously triangularize both matrices A and B, which is very important. This is, I think, what we covered last time. Anyway, so I have two matrices such that AB, such that they commute. And now we would like to show something. Show that if this matrix is, if B is nilpotent, right, then the determinant of A plus B is nothing else than just the determinant of A. So the determinant of A, sorry, yeah. Correct. Not B. The determinant of B will be 0. As you can see here, the determinant of B doesn't even matter anymore if B is nilpotent. Anyway, when you add with the matrix and you take the determinant, doesn't really, you can just forget about it. So that's a thing. Okay, let's see how we're gonna prove this. Let's see the first part. And the first part, it has, in fact, I think you can do it directly. So I know that we have a nilpotent matrix. So if n is nilpotent, so I would like to go to the definition of nilpotent, of a nilpotent matrix. Then there exists, let's say, a k, a positive integer k, such that n to the power k is the null matrix. All right, what can you tell me about a nilpotent matrix? Is, for example, what is the determinant of a nilpotent matrix? Can you tell me? Or in fact, well, I can ask you even more, but first, what about the determinant? The determinant is what?
Is it some positive integer? None?
No.
No?
If you take the determinant, there it will be what? It's 0.
0.
This implies that the determinant is 0. That's one thing. Okay. Great. What about some other thing? What else can we say? Well, about nilpotent matrices. You remember we did this problem, I think I did it in one of the videos where I said if a nilpotent, and we did this for 2x2 and 3x3 matrices, and I did it in another lecture for n by n. If I have a nilpotent matrix, then what can I say? That n raised to the power, the order of the matrix will be the null matrix, right? Also, n to the power n is the 0n. So we've proved this by using Cayley-Hamilton. We've done it for 2x2, for 3x3, and also for n by n. Moreover, what can you say about the eigenvalues or of a nilpotent matrix? What can we say? Are what? Are equal? Are
Are they also 0?
exactly, are all 0. That's important because, well, this is from this fact it follows that n to the power n is 0. So you can say that the determinant of is 0, right? But this is more important. You can say that all of them are 0. So in fact,
is the trace
yes.
also 0? Oh, that means the trace is also 0 for all the eigenvalues.
Yes, exactly. The trace is also 0. So what can you tell me about, okay, now by the spectral theorem, the eigenvalues of the identity plus n are what? Are, well, 1 plus lambda 1, 1 plus lambda 2, 1 plus lambda n, where lambda 1, lambda n are the eigenvalues of n. So what can you say about the determinant? So the determinant of n, of the identity plus n, is nothing else than just a product. So it's the product overall 1 plus lambda I. But we know that the lambdas, the eigenvalues of n, are 0. So let me write it here. Lambda 1 is the same as lambda 2, is the same as lambda n equals 0. So this product will be what? Will be 1. That's it. That's exactly what we wanted to prove. You see, it's just a collection of facts, of well-known facts, and this will give you, well, of course, modulo the spectral theorem. All right. So that's the first part. And look at the second part. The second part is just a generalization of the first part. So I have two matrices. If I take B to be the nilpotent matrix, right? And A to be the identity, there you go. You obtain exactly the first part. So the second part is much more general. So let's prove this. Well, you can use the first part by doing some tricky manipulations, but I don't want to do that. In fact, I don't even remember the trick. So I just want to do it by using some theory. So you know how they say you kill the mosquito with the atomic bomb. So that's what I'm trying to do. So let's put some theory on this problem. So remember we said something last time that if two matrices commute, they can simultaneously, both of them can be simultaneously triangularized, right? So let's write that. Since AB is the same as BA, right? It follows that let's see, what does it follow? So it follows that the A and B can be are simultaneously, let's write it, are simultaneously triangularizable, right? Which means that there exists a unitary matrix. So, Aaron, you're talking about some unitary matrices. Well, so there exists a unitary matrix, and then with complex entries, unitary. So it's unitary such that T1 is U star AU, and T2, let's denote this by T1 and U star BU. So these two guys are both triangular. So that's what the theorem says.
Can I ask something real quick?
Yes, please.
So wait, these unitary matrices are indexed in the complex plane?
Say that again.
You say these unitary matrices are indexed, or like I guess, are from
yeah,
the
they're you know, unitary means that U star is the same as U star. U is the identity.
Right, that's just like an algebraic expression though, but their values are all complex, is what you're saying?
Correct.
Okay.
All right. And now what I'm gonna say something is that, well, moreover, not just that, but remember I said some moreover, we have something even more. T1 has the eigenvalues of A, they're not just triangular, but on the eigenvalue, on the main diagonal of each matrix of T1 and T2, you will find the eigenvalues of A and the eigenvalues of B. So moreover, T1 has the eigenvalues of A on its main diagonal, and T2, so the second matrix, has the eigenvalues of B on its main diagonal. Right? Okay. All right. But now, since B is nilpotent, we said something earlier. Since B is nilpotent, what can you say about the eigenvalues of the nilpotent matrix?
There's zero.
We said exactly. It follows that all its eigenvalues, are zero. And thus, for example, T2, right? T2, you see, because T2 has this expression here, look at it. So T2 is this guy here. So it's U star BU. So it follows that T2 has only zeros on its main diagonal. Okay. So since it has, so it follows that. Now we have. So we like to get some information about the determinant of A plus B. But now we have, if we add, look at these two expressions here. So I know T1 is A star U star AU, and T2 is U star BU. But now if you multiply by, you know that U star U is the same as U star equals the identity. You can multiply by U on the left with T1 and also T2. So we get U T1 is the same as AU. Now you multiply by U star on the right, and then you'll get something like this. So we have that. Okay, in fact, I'll write it like this. A plus B is the same as U, and you can factor here T1 plus T2 times U star. Okay, so we have this relation as well. Anyway, I'll leave it to you as an exercise to figure this one out. I just told you. Just multiply to the left, the right by U star, whatever. So this implies that if we take the determinant, so by taking the determinant, this implies that it follows that that the determinant of A plus B, well, it will be equal to what? It will be the determinant of T1 plus T2, right? Because you know that the determinant is multiplicative, so the determinant of U times T1 plus T2 times U bar, it's the determinant of T1 plus T2 times the determinant of U star, right? But U star is the identity, so it's just the determinant is 1. So we have this. All right, that's great. But there is something about this, and we said something about T1 and T2. Both of them are upper triangular, or right, or whatever. And moreover, T1 plus T2 will be upper triangular. So, and we said that the T1 has the eigenvalues of A, and T2 has the eigenvalues of B, right? But T1 plus T2 is an upper triangular matrix. Right? So since this is an upper triangular matrix, and T1 plus T2 has the eigenvalues of A plus B, but the eigenvalues of B are 0, so T1 plus T2 has the eigenvalues of A on its main diagonal. On its main diagonal. But when we have, keep in mind that when we have a triangular matrix, the determinant of a triangular matrix will be the product of the elements. Usually this happens. So the determinant of a triangular matrix is the product of the elements on its main diagonal. So, but on the main diagonal are the eigenvalues of A. So you know usually that the determinant of a matrix is the product of the eigenvalues, and there you go. So finally, we have that the determinant of T1 plus T2 is nothing else than just the product of the eigenvalues of T1 plus T2, but the eigenvalues of T1 plus T2, well, the product of the elements on its main diagonal, right? But the elements on its main diagonal are the eigenvalues of A. So keep that in mind. By using this, it will be nothing else than just the product of, and this is nothing else than just the determinant of A. And that's it. That's the end of the problem. Is it clear? Very beautiful problem, correct? Jack, is the problem clear?
Yeah, I like this one.
Very nice, right? So keep this in mind, Jack. I think you missed the last lecture. Did you see the video?
Yeah.
All right. So I'll do a bunch of techniques there. In fact, I did a lot. Yeah, it's quite a long solution, but it's yeah, I agree with you, Timothy. Anyway, I would like to do one more problem. Yes, I would like to do one more problem. But one more comment I would like to make here is that I would like you to go on my previous lectures. You will see a bunch of techniques, and this will just it's another application. Well, I didn't have time to discuss it in the lecture on Tuesday, but also I wanted to leave some of these kind of problems for the recitation as well. Okay.
Very quickly,
Yes.
just in general, when you're if I were to take this exam, is the best strategy to try and just memorize as many of these theorems, like the theorems that you introduced on Tuesday?
You have to know them. Yes, you have to know these theorems. You see, that's the funny thing. Some of these theorems that I'm showing you are not done in any undergraduate course, unfortunately. And you'll see in analysis even. So you have to know a bunch of things, like to understand them, I would say, not just to memorize them, to understand them, where they come from, and then the statement.
How to apply them? Yes.
Yes. The statement will come at the very end, and then to know how to apply them. So you need to kind of have some kind of understanding of these results. So
hey, Lupu,
yeah.
I have a quick question.
Yes.
Do you have a lecture specifically where you went over unitary matrices other than the last one?
Well, not quite. Unitary matrices, more you discuss about unitary matrices, more in a graduate advanced level course. So more like this. Anyway, let me do one more problem. And in fact, I have two problems that I want to do, but I think I'm going to go with this one. So problem number, it's also on my list. So it's problem number 4. And this will be a quick one, because you'll see it was an international math competition, I think, in 2014. You know, that worldwide Putnam that I was just saying. And it says the following: let this matrix A with these entries A, I, J. So it's an n by n matrix. So from, right, it's a symmetric matrix, be a symmetric matrix, and symmetric metric n by n. n by n matrix with real entries and let lambda 1, lambda 2, lambda n denote its eigenvalues. Show that we have the following inequality. So the sum over all ij, right, of aii of these elements, ajj, is greater or equal than this sum. Lambda I, lambda j, with 1 less than I less than j less than n. Okay. So that's the one problem that I would like to discuss, and I think I'm going to stop here afterwards. This is in fact related to another problem that I wanted to do, but it looks like I don't have time to do it. Basically, it's just an application of a trace inequality. When you have a matrix, a symmetric matrix, well, first of all, I would like to ask you something. When you have a symmetric matrix, what do you know about the what can you tell me about this, the eigenvalues of a symmetric matrix? How are the eigenvalues of a symmetric matrix? I think we've done this. What can you tell me?
Are they like located on the diagonal?
Nah, I wouldn't go that far.
Are they real?
They're real. So the eigenvalues, keep that in mind. In fact, so the eigenvalues of a symmetric matrix are real numbers. Keep that in mind. We said this, and we said that the eigenvalues of a skew symmetric matrix are purely imaginary, right? All right, so now let's see. What if, so this inequality, if we square it, right, you see we have this ai, aj, lambda I, lambda j. So if we square this, so the inequality, the given inequality is equivalent with what? With well, if you square this, so you'll have yeah, okay. You'll have what? You'll have that this will be equivalent with the sum over all I squared plus 2 this the sum of this over all I less than j then ajj, right? And this guy will be in fact, no, let me put it like this. Let me start with this. So, okay, this is the first thing. So we know that, we know what? We know that the trace of A is the sum of the elements on the main diagonal, right? But also is the sum of the eigenvalues. Okay, beautiful. Now squaring this, which is equivalent with so this will be equivalent with what? Will be equivalent with the sum of aii squared, right? Plus 2 sum of aii ajj, right? Something like this with for all I less than j. And this will be equal to the sum of lambda I squared plus 2 the sum of lambda I lambda j. And now, with I less than j. And now keep in mind what we have to prove. So our inequality will be equivalent with our inequality, our given inequality is equivalent with our inequality is equivalent with what? With well, the sum of aii squared is less or equal than the sum of lambda I squared, right? So we have to prove this. So if we prove this, then we're done. But now what we're going to do, so that's what we need to prove. But now we're going to do the following, but you will see how simple this is. But the trace of a squared, so I'm going to look at the trace of a squared, right, is the sum of the lambda I squared, right, which is less or equal, right, wait, just a second. Now let me do it like this, but the sum of aii squared is less or equal than the sum over all iaj squared, right? Well, anyway, the sum over all aij of aij an absolute value squared, right? And this is what we call the oh my. This is what we call, is defined to be what we call the Hilbert-Schmidt norm, AA star. So this is what we call the Hilbert-Schmidt. Well, you can actually prove that this is less than trace of A. So trace of A squared is the same as AA star. But at this point, we know that the matrix is symmetric, right? Since the matrix is symmetric, AA star is the same as A squared, right? Which is nothing else than the trace of A squared. Agree with me? Because since A is symmetric. That's it. Problem ends here. And since the trace of A squared is, this guy is nothing else than the sum of the eigenvalues squared. And there you go. You prove the inequality. And that's it. You see, that's the big thing that saved the day, was this guy that's symmetric. So AA star is the A squared. But usually, I want to point out something. Let me point out this remark. And with this, I will stop here. In general, an inequality holds true. So in general, one can show that one can show that what? That that the trace of AA star, so the Hilbert-Schmidt norm, right, is less or equal than the trace of A squared. Well, when the eigenvalues are non-negative, and anyway, so you can show this by just using an application, just an application of the Cauchy-Schwarz inequality. Anyway, I'll leave this to you as an exercise to show this. So if the eigenvalues, let's say, are positive, but I don't think you need that. The eigenvalues are real numbers, then the trace of AA star is nothing else than, is less or equal than the trace of A squared. And in fact, the equality holds true for normal matrices. I think I told you in the lecture that we have equality when, if and only if this A is a normal matrix, which means that AA star is the same as A star A. Anyway, I'll leave this to you as an exercise. This is just an application of Cauchy-Schwarz inequality, and I think I'll stop here. I apologize I went over time, but I wanted to show these kind of techniques. Okay, guys, I think this sums up everything that we have done in linear algebra. Next week, we will start talking about analysis, and well, we have plenty of things to do in analysis. Thank you very much. Bye-bye.